Welcome to this video on PCB Traces 101. In this video, we'll explore the basics of PCB traces, looking at their properties, how to size them, what guidelines I would suggest when you're just starting out with PCB design, and some areas for you to explore deeper into with some suggested references, for example, control impedance, delay matching, and so on. Along the way, we'll be looking at some examples, examining some real-world designs, looking at why these signal traces are this specific size, why power traces need to be wider, why they are spaced a certain way, and so on. We'll also look at some various resources, such as calculators, which will help us make informed decisions on how to size and space our traces, for example, also looking at their basic properties, such as resistance, inductances, and so on. A huge thank you to Altium for sponsoring this video. Although the tips in this video are generic and can be applied to any design software, I use Altium Designer in my personal and professional life for all of my designs. If you'd like to give Altium Designer a try, make sure to check out the link in the description below, or go to altium.com/YT/PhilsLab, and you can get yourself an Altium Designer free trial with Altium 365, as well as 25% off your first license purchase. Keep in mind that this video covers the very basics and the essentials, and there's far more to this, but I'd like to use this video to expose you to the main ideas. With that being said, let's get started. Traces, as you are probably aware, are conductors, typically copper, that connects elements on a printed circuit board together. This could be from an IC to another IC, it could be from a connector to an IC, passive components, and so on. When we're considering traces, and this is a typical beginner mistake, beginners might just use one size, have them very closely spaced together, but this is typically not how a more experienced person might design their PCB. When it comes to traces, although it might look simple, just a connection, there are many different types and parameters, for example the width, thickness, the length of the trace, the material of the dielectric underneath the trace, or the material of the trace itself, as well as if it's a single-ended trace, if it's a differential pair of traces. Also, not just the trace geometry itself, also the spacing from trace to trace, or trace to hole, and so on, the distance to the return path, if it's rooted on an external layer or internal layer. All of these different types of traces and parameters, especially for more advanced designs and high-speed, high-frequency designs, you really need to take these parameters into account. We need to take these parameters into account. This is with respect to power delivery, or if we're looking at signal traces, what kind of current levels we're looking at, voltage levels, the maximum frequency content of the signal, the way we route our traces and the materials we choose might influence the propagation delay. We have design constraints, maybe manufacturing constraints, and so on. So although the basic statement saying that it's a conductor, that a trace is a conductor that connects elements on a printed circuit board is very much true, there's far more detail to that, and people beginning with PCB design are usually not familiar with this. We need to, of course, consider this because of power integrity reasons. We want proper power delivery, especially for high-speed ICs, for signal integrity reasons, electromagnetic compatibility, so EMI and EMC, as well as, of course, manufacturability, which is incredibly important when it comes to PCB design. You'll hear me saying this in other videos as well, but I'd like to reiterate the point that a trace is not a singular element. We typically always have a forward path and a return path, and the electrical energy is actually contained in the dielectric space around or between these traces. To illustrate that many different sizes of PCB traces and planes are indeed used, we'll be looking at, for example, this FPGA-based audio DSP development board I designed. This contains numerous ICs, both analog and digital, high speed, power, and so on. And you can see we have various different traces and trace sizes. We have rather thin traces, which might be these signal traces. They're routed in a certain way, maintaining space. But we also have these thicker traces that might be for power. Or we might have internal power planes, which are effectively very wide traces. We as PCB designers have control over trace sizing or trace geometry, as well as many other aspects, for example material selection and so on, which we'll get to later. The defining parameters of a trace typically are its width, and on the right-hand side we can see two different types of traces. On the left-hand side we see a microstrip or external layer trace, the referenced plane below, separated by dielectric material. On the right-hand side we have a strip line or an internal layer trace, where we have two sets of reference planes with a trace buried in between, so to speak. As PCB designers, we have pretty much full control, along with the manufacturer, about these geometries. The main aspect of a trace is usually its width, and this is indicated by a small w. Typical widths, of course this is a typical, we can have other extremes as well, are typically very small 0.1 millimeters, for example if you're doing a BGA fan out, anywhere up to, let's say, a millimeter or more, of course. Again, these are typical widths. The width, we shouldn't just choose as one width and go with that for the entirety of our design. It depends on the application. If it's signal traces, if it's power, something called control impedance, which you'll see later, and so on. Other than width, we can also determine the thickness we want for our final PCB, and this is something we have to communicate with our manufacturer and talk to them what's possible. Same goes with maximum and minimum trace widths. The thickness typically for an outer layer trace will usually be 1 ounce copper, 1 ounce per square foot, which is about 35 microns. That's a typical final thickness. An inner layer trace, you can get them as 1 ounce default as well, but typically will be ½ ounce copper. You will choose your thickness depending on what current carrying capabilities you need, minimum trace widths, so typically a thicker copper foil will have larger minimums and also will be a higher cost. I'll talk more about this a bit later as well. We also have the length, which we can effectively play around with, although this is usually fixed by the design. We can alter the length, but what we should do is, unless there's a specific reason to, keep our trace length as short as possible. This is for power and for signal, and we'll see later why that is. Longer and also narrower traces typically have more potential for EMI, so electromagnetic interference, that is both from an emission standpoint as well as susceptibility, as well as longer traces, especially if they are parallel runs, we might have crosstalk problems as well. So trace geometry is incredibly important. We need the width, the thickness, and the length. There are, of course, also other parameters, such as the surface finish. So for outer layers, you're not just going to have pure exposed copper. We'll have this plated, we'll have some sort of surface finish, for example, ENIG, Hassel, and so on. That will influence the shelf life, solderability, RF performance in certain cases, and so on. Again, we also need to decide between inner and outer layer. We might have benefits putting on an outer layer in terms of thermals, but for an inner layer, we might get better shielding properties, might depend on controlled impedance, what bandwidth our signals have, and so on. Also, aspects to trace geometry are, of course, spacing to reference planes. In the top right, we can see we have H, or H1 and H2, which are the electric thicknesses, which also influence, of course, the spacing between trace and plane. The material selection, so what dielectric constants we have, also influences our controlled impedance, it influences maybe the field spread, dissipation factors, and so on. This all sounds very complicated and is rather daunting if you're just starting out with PCB design, but at the end of this video, we'll look at some simple guidelines just to get you started and headed in the right direction. As a quick illustration, your trace sizing will also determine the cost of the PCB and what materials you choose. To do so, let's look at the PCB website, a very typical PCB manufacturer. We'll look at, for example, a 4-layer PCB. We have different selections of materials. If we, for example, choose a material that's a higher frequency, so for example, this Rogers is great for RF design, that will influence the cost quite significantly, as well as different FR4 glass transition temperatures will change the cost depending on your requirements as well. The minimum track size, as we saw, will also influence the cost. So if we have a narrower track size, this will be harder to manufacture and thus bring up the cost as well. Same goes for surface finishes, and this of course needs to be taken into consideration when you're designing your product. When we're looking at trace geometry, we need to wonder why this actually changes the electrical properties and how this does. In particular, the width, thickness, length, and spacings and so forth predominantly change the resistance, inductance, and capacitance of those traces. On the top right-hand side, we can see a typical 3D illustration of a trace separated by a dielectric material of thickness H above a reference plane, so a typical external microstrip trace. As we're using a conductor, the conductor itself will have some sort of resistivity, and from the resistivity and the geometry of that trace, we can figure out the resistance. The resistance is important predominantly for DC characteristics, so if we're running a long, narrow trace, we can expect significant voltage drops, heating, and reduced current handling capabilities. From school physics, you'll probably remember the formula R equals rho times L over A, which gives resistance, which is dependent on the resistivity, which is a material property, the length of the trace, as well as the cross-sectional area of our trace. Now, as illustrated in the top right-hand side, PCB traces aren't rectangular, they're actually trapezoidal usually, but let's just take this as a simplification, that the area is simply the thickness, the trace thickness, times by the width. So trace material resistivity is pretty much always the same. We're mostly using copper. The length we can vary, so a longer trace will increase the resistance, therefore increasing potential voltage drops, increasing heating. If we increase the width, that will of course bring down the resistance, and if we increase the thickness, that will bring down the resistance as well. And this nicely illustrates how trace geometry impacts resistance. However, with PCB design, we're not just concerned about DC characteristics, we're looking at AC characteristics as well, and that's where inductance and capacitance comes in, and especially for high-speed, high-frequency designs, this becomes incredibly important, as well as for power delivery. Inductance typically is to do with the properties of magnetic fields. On the bottom right-hand side, we can see electromagnetic fields that surround typical traces. So on the bottom left, we can see a microstrip, an external layer trace, we have a trace, and a reference plane below. The electric field are the blue lines, and the red lines are to illustrate the magnetic field. On the right-hand side, we see the same thing for a strip line or an internal layer trace, where we have a plane, trace, and plane. Inductance of a trace can be a bit difficult to compute. There are a few different approximations. For example, this one here, which I took from allaboutcircuits.com. There are many different calculators to help you do this, and we'll look at some in just a second. This one actually doesn't take into account the trace thickness. This is again an approximation, but what we can take away, that inductance is to do with loop area, very simply speaking. So if we increase the thickness of our dielectric, we increase the loop area, and we have a higher inductance trace per unit length. Typically, you'll see that low inductance is desirable. It improves power delivery, it reduces the size of the magnetic field, and so on. Lastly, trace geometry also influences the capacitance of our trace, or the capacitance per unit length. Again, this is an AC property, so important also for power delivery, signals, and so on, but typically somewhat of a lesser concern. Of course, this is a big generalization compared to inductance. Capacitance has to do with electric field, and thinking back to school physics again, the capacitance, for example, for a parallel plate capacitor, is approximately equal to the permittivity times the surface area divided by the distance between our two plates. Increasing the magnitude of the dielectric constant, increases the capacitance, increasing the width of our trace, increases the capacitance, increasing the length, increases the capacitance, but actually decreasing the spacing, so reducing H, for example, increases the capacitance. And this decreased spacing is actually very helpful for closely spaced power and ground planes for power delivery, which gives us high capacitance and low inductance. Slightly more on that in just a second. All this just to illustrate that trace geometry has severe DC and AC impacts, and we need to take care of that for power delivery, signals, and so on. As important as signaling is in PCB designs, power delivery and power distribution network design is incredibly critical in many designs as well. This is especially true for high-speed digital, where we need to supply quite a large amount of current, quite a large amount of energy in a relatively short amount of times to these fast-switching ICs. Again, to deliver power and energy, we use traces and planes, and we need to size these traces and planes appropriately, both from a DC and AC standpoint. For power delivery, the first thing you probably think of is the current handling capabilities, as well as the thermal properties, making sure our PCB, our conductors, don't overheat. To do so, there are many different calculators online, and I'll guide you through one in just a second. Typically, from the IPC-2221 standard, we can also get various calculators. I'll show you in just a second how we arrive at these numbers, but for example, for an external 1 ounce copper thickness trace with an allowed maximum temperature rise from ambient, so 10 degrees in this example, for a 0.3 millimeter width trace, we get a certain resistance per unit length, which we saw on the previous slide, and through one of these calculators, that gives us about 1 amp of allowed current. So that's quite considerable given a very, very thin trace at only 0.3 millimeters. When we come to the inductance section, we'll see why you should actually increase the trace width, or even though the current handling capabilities are fairly decent. Of course, this is entirely design dependent. If we double the trace width, we get up to 1.6 amps. Let's go over to a calculator now to see how to use this for yourself. There are many different tools online. I just Googled IPC-2221 Calculator, and this is one of the first pages that came up. You'll typically have some sort of design requirements, for example, maximum allowed temperature rise, what the ambient temperature is, and what current you need to sustain. So let's say we have 1 amps, we're using an external layer trace, we're using a final trace thickness of 1 ounce per square foot, which is the same as 35 micrometers. Temperature rise 10 degrees, ambient temperature 25 degrees, and let's just say we have a 10 millimeter trace length. You'll see we have two different results. One is for internal layers and one is for external layers in air. For internal layers, you'll see we'll need about 0.8 millimeters, and for external layers, we'll typically need 0.3 millimeters. So quite a narrow trace width for external layers, given the same current handling capabilities for a given temperature rise. And this is because the external layer is exposed to the surrounding air, and we have the advantages of convection, for example. We can also see resistances, voltages, and power drops, so it really pays off to just play around with this calculator, see what traces we might need for, let's say, 10 amps, and what resistances and voltage drops that would give, also for different allowed temperature rises that we can get away with thinner traces, and so on. So current handling capabilities, the DC aspects, for example, to do with resistance, voltage drops, and so on, is something I would look at probably first when it comes to this kind of power delivery area. As I said before, for high-speed digital design and power delivery in general, we are also concerned with inductance. On the bottom right-hand side, I've drawn a very simple power distribution network. in its somewhat non-ideal form. On the left-hand side, we have a voltage regulator module. Let's say this is our power source, maybe feeding into a buck converter. On the right-hand side, we have a load modeled as a current source. The regulator itself will have some inductance, will have some output resistance, and so on. So simplifying that, I've just put it as an output resistance. These interconnects, for example, these series resistances and inductances, are to model traces very simply. We talked about resistances, but also the inductances. And inductances are incredibly important for power delivery. Effectively, higher inductance mean we have higher resistance, very simply speaking, to rates of change of current, and it will become harder and harder at higher frequencies to deliver the amount of current we need to our load, to our ICs. For example, for an external 0.3mm wide trace, 1 ounce copper on a multi-layer PCB, so given fairly thin dielectrics between forward path and return path, the inductance per millimeter turns out to be 1 nanohenry, and at high frequencies, that can be quite significant. And that can lead to very serious problems if we don't design our power delivery network right. To get these values, you can again look for Trace Inductance Calculator. They'll use some approximate formula for these very simple ones. There are, of course, more advanced tools, but it definitely pays off to play around with one of these. The numbers we just saw come from this as well, so we get about 1 nanohenry for this trace geometry. If we, for example, double our trace width, so from 0.3 to 0.6 millimeters, we get quite a significant, so half effectively, reduction in our trace inductance. Remember I said trace inductance has to do with loop area, so if we increase the substrate height, we can expect the inductance to increase, as we see here. Same thing goes for increased trace length. For a longer trace length, we increase our inductance. This is why in power distribution systems, we will typically use wide traces, something like so. This is a 0.6mm trace, and you can see immediately this is a power delivery trace compared to these thin signal traces, and we also want to keep them as short as we can. Length has to do with inductance pretty much directly, therefore we want wide traces, short traces. And this is true for decoupling, it's true for the whole power distribution network. That's why, for example, on this op-amp, we have a power input pin, we want to place the decoupling capacitor close, and we want a wide, short trace going from the decoupling capacitor straight into the power pad. Oftentimes, rather than using a trace and a ground plane, we might use a set of closely spaced power planes, so a power plane and a ground plane together, to really reduce the inductance of those set of planes and really improve our power delivery at high frequencies. And there'll be a future video on this. But this is why in a lot of higher speed digital designs, you'll see power planes used very close to adjacent ground planes for low inductance, low resistance power delivery. So far, we've pretty much only discussed single-ended signaling, single-ended traces with a single forward path and a return path. There are also a class of traces which constitute differential pairs, and that's a huge topic in itself, and I do actually have a video on that. In this video, which is on my channel number 83, I go through single-ended versus differential signaling basics, what a PCB differential pair looks like, what to pay attention to, and controlled impedances and so on, and I'll leave a link to this in the description below. If you just started out with PCB design, or if you've been doing it for some time, you might have already come across the term controlled impedance. Controlled impedance is incredibly important, and you need to know about this as a PCB designer designing modern systems. We'll cover the basics here, but I'll link you to some references at the end of this section. Very simply speaking, controlled impedance is typically necessary for high-speed digital designs, as well as analog, for example, RF designs. We need controlled impedance for digital, high-speed digital meaning short rise and fall times, which result in a large bandwidth, and RF meaning a high frequency. This doesn't really tell us much when we need controlled impedance, but let me show you briefly what is meant by critical length, which also comes up a lot when we're talking about controlled impedance. There are many resources on defining when something is high speed, what is meant by critical length, and there are various different definitions of this. I'll leave a few links to these various resources in the description box below. Effectively, we need to be concerned about controlled impedance when the connection, our trace length, is long compared to the wavelength of the maximum frequency of interest within our signal. This is when we get a changeover from looking at our circuit elements and our traces as lumped elements, and when we move over to the realm of distributed elements. And this is where we need to take care of impedances and so on. There are also calculators for this, so telling you at what trace length you need to take care and when you need to start controlling impedances, and this again depends on material properties, it depends on your rise and fall times, your data transfer rates, and so on. This calculator from Sierra Circuits I'll leave in the description box below. For example, for an external layer trace, we type in the dielectric material constant, typically a number around 4. We can type in our maximum data transfer rate, so 1 gigabit per second, for example, for gigabit Ethernet, and we can click on Calculate, and that gives us our fastest signal rise time in nanoseconds, so this is very fast, 140 picoseconds, and our maximum frequency content, which leads to a critical length on the right-hand side to about 12 millimeters. So once our trace length is 12 millimeters or above, we need to start controlling our trace impedance. So as you can see, that's already after about 1 centimeter. The problem gets worse if we go to higher data rates, so 2 gigabits per second, that already halves our critical length and so on. We have similar calculators, of course, also for the RF domain. To gain more understanding about the rise time and frequency content of signals, I'd highly recommend watching video number 64 on my channel, which is PCB design for EMI and signal integrity, telling you all about this as well. In any case, now we've explored briefly when controlled impedance is needed, but the question is also why. Typically, for signaling, we might have a driver with a certain output impedance, we have our connecting trace, and we have a load, which also has its own impedance. Also, thinking back to school physics, remembering the maximum power transfer theorem, if our impedances are matched, we get maximum power delivery. If there's a mismatch, we lose power, and we also get reflections, which can lead to signal integrity and EMI issues. Therefore, we want to match our driver to our trace and our load impedance. Controlling impedance of a trace, again, is simply done by trace geometry, materials, and their properties. We won't be going to many details here. This is simply meant as an exposure to these topics and for you to dig a bit deeper in the various resources I will leave below. There are various configurations we already saw, for example, microstrip, which is an external layer trace, a strip line, which is an internal layer trace, and there's many more. For example, coplanar, embedded, symmetric or asymmetric strip lines, and so on. In terms of further resources, I do have a rather old video on my channel. That's video number 3. I plan on making an updated video on controlled impedance, but check that out to get the basics. As well as on the Altium Academy YouTube channel, I've created a video on PCB stack-up and controlled impedance, specifically the Altium Designer, which I'll leave in the description box below as well. Again, keep in mind we're just broadly covering the topics that are to do with traces, and I'll explain more in detail in future videos, as each of these topics is worthy of a video in its own right. Looking at PCBs and looking at high-speed digital PCBs, you will probably have seen these various squiggles or meanders on traces. These are very important and are there to introduce delays and to match delays, for example, within a bus or within, for example, a differential pair. Again, you'll see this in high-speed digital designs, for example, using DDR memory, PCI Express, USB, and so on. And these squiggles and meanders are there to match delays by tuning it to the trace lengths effectively to ensure correct timing, for example, at the receiver, plus minus an allowed timing margin. The signal speed, or the speed of the electromagnetic fields, differs depending on the dielectric material, differs depending on the trace geometry, as well as the loading. We can make a simplification, saying that the trace propagation delay per length versus the dielectric constant is simply the square root of the dielectric constant divided by the speed of light. Therefore, we can't just match the lengths of all these tracks. If we're routing, for example, an outer layer trace or an inner layer trace, we need to take care that the propagation delays per unit length are different depending on how we route them and our geometries. For example, for an outer microstrip trace, we might get a propagation delay of 6.1 picoseconds per millimeter, whereas for a strip line trace, an inner layer trace, we might get a propagation delay of 6.7 picoseconds per millimeter. Again, we can do this within a bus or within a differential pair, so inter or intra-pair skew or delay matching. I do actually have a fairly recent video on this. This is video number 110, which goes into far more detail on high-speed delay matching, and I'll leave a link to this again in the description box below. Finally, let's talk about some guidelines. I know a lot of this video was quite theoretical, but I'd like to show you some practical tips that you can implement directly in your PCB designs that will give you a significant improvement if you haven't taken particular care about trace sizing, spacing, and so on before. The first thing is to size traces appropriately for the application. So not one trace size for all signals and all powers and so on. Do it depending on the signal type, if it's power or not, if it requires controlled impedance and so on. Importantly, stay away from manufacturing minimums. If you go to your chosen manufacturer of choice, for example, mine is PCBWay, I can go to their capabilities section and look at their standard capabilities, and they can do traces down to 0.1 millimeters with a spacing of about 0.1 millimeters. On the right-hand side in the remarks, you can also see they strongly suggest to design above 0.15 millimeters to save cost. And this is very true because it's hard to manufacture small and narrow traces, and therefore that will drive up the cost. So even though they can do 0.1 millimeter traces, stay away from that. Go to 0.15 or even 0.2 millimeter traces, unless you have a specific reason to go down to 0.1 millimeters. When sizing traces, other than staying away from minimums, of course, you need to consider all aspects. Are we delivering power? If so, we need to think about DC loss, about thermals, or inductance. If we're talking about high-speed digital or RF, we need to consider the signal bandwidth. If we do need to control impedance above a critical length, there are effects such as skin effect, which introduce extra losses, or we have different material types, and so on. Again, don't just use one size for all. If you don't have a particularly constrained design, for example, a simple microcontroller project, I have some recommended trace widths that I'll start out with, for example, for a 2 or 4 layer board, which doesn't have controlled impedance and so on. But again, it always depends on the application. Take these recommendations very lightly. Typically, I will use 0.2 to 0.3 millimeter trace widths for signals and 0.5 to 1 millimeter for power. For example, looking at this FPGA board again, I've used fairly narrow traces because this is actually an impedance controlled board of about 0.13 millimeters, and these are all my signal traces. And if I already have controlled impedance in the design, I'll make sure that pretty much all my signal traces, if I can, are routed as controlled impedance traces. For low-speed power, for example, just going to an LED, this is probably a bit overkill, but I, of course, widen my traces. I go to about 0.3 millimeters. Remember, reduce our DC drop, reduce the inductance, and this is for fairly low-speed, not very critical power delivery. For power delivery, for example, from my buck converters on the left-hand side to the FPGA itself, I use power planes. So these are as wide as I can make them and close to a ground reference plane. Closely spaced means low inductance, higher capacitance, and wide I reduce my inductance and reduce my resistance. As you can see, I didn't just use one size fits all for these traces. I did it depending on if it's analog, if it's digital, if it's power or not. What we also want to do, other than widths, is also minimize the lengths, and we want to avoid long parallel runs. I'll do a future video on this where we talk about crosstalk, but that's a huge problem if we have long parallel runs of traces. Also, minimizing lengths helps with EMI, reduces our radiative signature, reduces susceptibility. We can see that here as well. We have the FPGA in the center. On the left of it, for example, we have this HyperRAM module, which is fairly high speed. Looking at 2D view, that's why I've placed these modules so close together, is that I can minimize the trace length between these two parts. Anytime I have lower speed signals, for example, just going to some buttons or some switches, these are fairly long traces because they are effectively DC. But any high speed signaling, I try to keep as short as I can. With regards to current carrying capability, if possible, increase the width of the trace before trying to increase the thickness. Remember, we saw increased copper thickness increases the cost of the board, increases the cost of manufacturing, and places additional constraints on the minimum width of your features. So increase the width or use planes instead if you require current carrying capabilities higher than usual, and only if you have to increase the copper thickness. You have to balance cost, thermal properties, DC drops, and so on, of course. Not just sizing is important for traces, but of course also spacing. This is oftentimes something I see in very beginner designs, is that traces have simply just the narrowest space allowed between them, so the absolute manufacturing minimum. So again, stay away from manufacturing minimums, increase the spacing. The IPC guidelines suggest, for example, for stripline traces, is for a dielectric thickness of H, space out your traces at least 1H apart. For external layer microstrip traces, that becomes 2H, but my suggestion is space your traces as far apart as reasonably possible. If you have the space, use it. Of course, there's also special considerations for high voltages. So for multiple 100 volts, and the higher you get in your voltage, the further apart your spacing needs to be. And there's specific IPC standards for that as well, again reserved for a future video. Spacing is not just trace to trace, it's trace to anything else. It's trace to copper, it's trace to hole, it's trace to board edge, and so on. This is incredibly important and one of the biggest beginner mistakes I see. For example, looking at the stack up of one of these boards, looking at layer 1 to its return path below, we have a dielectric thickness of about 70 microns. So according to the IPC guidelines, we want at least 0.14 millimeter spacing for an external layer trace. But let's go to the PCB. We can do measurement between these traces, and we have about 0.4 millimeters, so far wider than the IPC suggests, but this is what I always do. Maximize the spacing between features, so that's vias, its pads, its traces as far as you can and as far as is reasonable. And this is true for every bit of routing I do, unless you're very, very space constrained. So maintaining spacing between all traces, pads, vias, and so on as reasonably as you can. Not just, for example, grouping traces as narrow as you can together. This isn't great for the reasons we discussed previously. What's also incredibly important is, unless you have a reason otherwise, is to maintain a proper return path at all times. Proper meaning there are no gaps underneath the trace, it's closely spaced, and the return path below is wider than the trace. If you remember back to the first few slides, looking at the electromagnetic fields, is that they spread out. So if I look at my top layer, and if I show the view of my return path, which is this orangey color underneath, which is this ground plane, all my traces are routed above a solid reference plane. No cuts underneath. The traces have a wide enough return plane underneath. I'm minimizing my voids, and I always make sure I have a solid return plane regardless of where I am. Finally, we also have to consider inner versus outer layer routing. As we saw before, inner layer we have typically reference planes above and below, which can increase the shielding effectiveness. We get better containment of fields. This is great for high-speed signaling. It's great for sensitive signals and so on. So these are some very basic guidelines, and if you're following these, this is already a great starting point. Thank you very much for watching this video. I hope it was helpful, and I hope it gave you some basic insight of what considerations you need to take into account when you're looking at PCB trace sizing, dimensioning, spacing, and so on. If you like the video, please leave a like, a comment if you have any questions, and make sure to subscribe to stay up to date with any latest hardware, firmware, and DSP videos. Thanks again for watching. Bye-bye.